Good morning, everyone. So we begin with the first session today. Soeren will continue with his fourth lecture.
Okay. All right. So good morning, everybody. Welcome back. So today we're going to continue our discussion on non-equilibrium dynamics, and basically we're going to take off pretty much where we left off yesterday, namely in the discussion of these very interesting phenomena, these non-thermal fixed points. So what have we done so far? So we have somehow established this classical statistical simulation techniques and convinced ourselves that this is somehow applicable to study dynamics of really far from equilibrium quantum systems, states with somehow very high phase space occupancy. And then in somehow just running these simulations and looking somehow how a system that is put in a far from equilibrium state evolves towards its equilibrium state, we somehow unraveled this very interesting pattern that system doesn't just somehow relax to equilibrium right away, but instead somehow takes this other route, right, where sort of very quickly it forgets about the details of its initial state, and instead reaches somehow a state where it exhibits self-similar scaling properties for an extended amount of time, and that is what we call these non-thermal fixed points. Now, that's a very interesting behavior, right? We've seen examples of this happening in scalar theories. We also did it in a gauge theory. We essentially saw the same kind of behavior emerging, although the details were different, right? For instance, these scaling exponents, which are here called alpha and beta that we observed, they were different for scalar and gauge theories. And okay, I mean, of course, that's something we could expect, right? After all, the theories are somehow very different, right? But so somehow the point is that this is something that, well, I mean, essentially screams, right, for having sort of a simpler interpretation, right? I mean, you start with something very, very complicated, right? I mean, for instance, having these very strongly nonlinear fields going on, and all of a sudden the physics becomes very simple, right? And so, I mean, whenever something like that happens, right, you should have a chance to somehow understand these things a little better, right? Now the problem with that is somehow the tools that we have at hand so far, right, which are these classical statistical simulations, right? Well, they're really very powerful tools in the sense that, you know, after making the classical approximation, right, we don't have to make any further approximation. We can really study somehow the full dynamics non-perturbatively, essentially. So they're powerful numerical tools, but on the other hand, they also provide us somehow with rather limited physical insight, right? We know how to compute everything, right? But from just being able to compute, we don't really necessarily get a much deeper understanding, right? In terms of, say, for instance, what is actually, I mean, what is in a sense causing this scaling behavior, right? How can we understand the values of these exponents and so forth? And so kind of the storyline of today's lecture is going to be that we somehow need different theoretical tools to somehow, on the one hand, obtain further insights into this phenomena that we observe, right? And then, of course, there's also this big point that we already started to run into yesterday, right? This, after all, the world that we live in is somehow not entirely classical, right? It's, I mean, at some point it's intrinsically quantum, right? And so we would like to be able to also study non-equilibrium phenomena in the quantum regime, right? And so, where this is going to lead us, if eventually, is what we're going to be discussing is essentially kinetic theory today, right? Or kinetic description of these non-thermal fixed points in particular. And so in that sense, I mean, the title of the lecture is a little bit off today, right? I mean, this is not going to be non-equilibrium QCD dynamics on the lattice today, really, but it's going to be about non-equilibrium dynamics and somehow trying to understand the phenomena that we observe within these simulations from a somewhat different perspective. Okay. So how can we do that? And so somehow the first part of this, so the first part of today, we're going to be dealing with essentially how to get to a kinetic description starting from a quantum field theory, right? And then in the second part, we will analyze somehow these phenomena that we see within the context of kinetic. Okay, so far let's go back to somehow our overarching pillar, right? That we have always used to somehow study non-equilibrium phenomena, right? So we established somehow in the first lecture that essentially all the non-equilibrium dynamics that we're interested in can be encoded in this non-equilibrium generating functional, which is formulated here on this Schwinger-Keldysh contour, right? And so, okay, so what have we done, right? So we had taken this contour time ordered product of introducing 1-point and 2-point sources to our fields. And so, okay, what we went on, right, is then how did we get to the classical approximation, say, right? We constructed the path integral representation for this expression, right? And then subsequently expanded in H bar, to obtain a classical statistical approximation, right? And then we talked about the corrections and so forth. Now the point is, if you remember, for instance, the discussion that we had in the context of scalars, I already told you that, you know, the theories we're dealing in, at least in that context with, right, they're also incredibly weakly coupled. So that could be certainly of interest for studying scalar field dynamics. Well, when it comes to studying QCD, right, I mean, we know that perhaps at the scales that we're actually probing QCD in collider experiment, it's perhaps not that weakly coupled, right? But okay, I mean, nevertheless, we should be able to work out what's actually going on in the weak coupling limit, and so okay, I mean, so there's certainly motivation for do that. And so somehow the punchline of what we're going to do today is that if we're interested in weakly coupled field theories, right, then somehow H bar is not the only parameter that we can expand this thing in, right? But instead we should be also able to essentially perform a weak coupling expansion of this non-equilibrium generating functional, and thereby obtain, in this case, a perturbative, so an approximate description, but that should also be valid in the quantum regime then, right? So it's no longer expanding in H bar, so we can immediately keep corrections which are quantum as well. Okay, so how are we going to do that? And so usually you may be tempted here to say, okay, good, I take my action, right? Okay, action has some parameter lambda, right? I go and I expand, okay? I just compute order by order in the coupling. Now it turns out this is a little bit too naive, actually. The reason is that this a little bit too naive is somehow actually not that difficult to understand. So if you do this naive coupling expansion, then this leads to a phenomenon which is called secular divergences. So what do I mean by that? So secular divergence is essentially a term which grows with time. Okay, and so I mean this is a phenomenon that actually you can very simply understand already. At the simple example is just looking at the decay of a particle, say. Okay, so okay, say you have a particle which has a certain probability to decay, right? It's given, let's say, by coupling constant lambda squared, and then perhaps there's a higher order process which goes is lambda to the 4 or so, right? Then okay, so the change in time of that particle number, right, would be governed by these two decay rates, and in principle there could be higher order terms. Now, if I solved it, okay, now I can solve this, right? Okay, so I get an exponential decay in time. So okay, my particle number will decrease as a function of time, right? And life is beautiful. Now, if I somehow were to do a naive expansion in the coupling, right, what would I do, right? Well, I would first, at leading order, ignore everything that's on the right-hand side here, right? And so I would just have y dot of t is 0, right? Which would give me the fact that somehow the particle number that I have is just constant, okay? Then, if I really do somehow a strict expansion in the coupling, right, I would take somehow my leading order solutions, say whatever, my free propagator or something like that, right? I would plug that back in, basically, when now evaluating these nonlinear corrections. So at next to leading order, I would get an equation of motion which is something like y dot next to leading order is minus lambda squared y leading order. And so that would lead to something like y of t is y naught minus lambda squared y naught t, okay? And so what you can see here right away is that, okay, while at very, very short times, right, that of course provides a decent description of of somehow what is here in this case the non-perturbative solution to this problem, right? You can also see that somehow the regime in time that this kind of naive expansion is valid is incredibly short, right? I mean, as soon as somehow the decay of the particle has a significant effect, right, this expansion simply breaks down and is no longer meaningful, yeah? So in other words, it's somehow not a uniform expansion in time, yeah? And so, I mean, physically, this has a very, physically, this is somehow, this is very simply stated why something like that happens, right? And so the reason is simply that the state of the system, yeah, will change as a function of time as it evolves, right? Yeah? So in this particular example, right, particle decays, right? Likewise, the examples we've seen from field theories, right? Our scalar fields will decay, fluctuations will grow, right? And so somehow if we just do a perturbative expansion around freely evolved fields, that will not be very meaningful simply because the state of the system that we want to describe can change very dramatically, right? Now, how can we get around that? And in a sense, the answer is also, is to a certain extent also written here, right? Namely, what we have done here, in somehow getting to this kind of an answer, right, is we have actually not somehow considered this entirely perturbatively, but what we have done is we have perturbatively computed the corrections to the equations of motion, okay? And so really, what we need is, say, in perturbation theory, right, we always start from free fields, right? We don't need to know sort of what is the first effect of, what's the first perturbative effect of around free field evolution to certain observables or so. But what we actually need is we need to account for the coupling corrections to the equations of motion, right? So very much like this example here, right? So if I now interpret this as the equation of motion, I get this solution, right? And then you can see that, for instance, here the lambda to the fourth term will be almost irrelevant compared to the lambda squared term in this case. And so I get a meaningful expansion with decent convergence. And so as you can see, right, this expansion in a sense corresponds to some kind of selective resummations of an infinite order of coupling terms, right? So, if I expand the exponential, I will keep essentially all powers in the coupling. In this case, if this was somehow the processes and say the next term would here come at order lambda to the 6th, right? This would be formally accurate with the full theory at order lambda to the 6th. That's where somehow the next processes come in. So we're not somehow taking the full, not all processes into account, but we're taking a subset of processes, but then resumming them to all orders. So it's a selective resummation of essentially higher order processes. Or what one needs to do. That's what I'm arguing here should be done. Okay? Questions? Yes.
Is there any reason that odd powers of lambdas are not there?
This was something I just pulled out of my head, right?
Okay. There is no.
This is not. Lambda is not even. It doesn't even have a meaning here, right? I just meant to introduce some expansion parameter. Yeah. And typically, if you calculate the decay rate or so, it'll be powers of lambda squared. Because you need to compute the diagram and square it basically, right? And each diagram has one vertex, so that's typically what you would do. Okay, so how can we go about it? So really, what we want is we want to compute corrections to equations of motions of free fields, right? So that's what I argued here one should do. And so how do we do this in the quantum theory? And so really, the method to do this is to use effective actions. And so, in fact, I guess you're kind of familiar with this in the context of say, thermal field theory or so. Principal Rob was doing similar things, right? He was constructing a quantum effective potential, right, for his anonymous potential, right, for his Polyakov loop, if you want so, right? And so the spirit here is very much the same, right? We want to construct, right? So usually we'd have, say, our scalar field oscillating in its bare potential, right? But now we want to compute, say, first of all, the corrections to its potential, right? And so the way to do this is to use what is called effective actions. Okay, so just so I mean, you guys, who's familiar with effective actions? Who's not familiar with it? Okay, everybody's seen this. Okay, good. So then, okay, so then I can be rather brief here. Okay, good. Okay, so how does one construct these effective actions? Okay, so beforehand we had our generating functional here, which is our old friend, right? Okay, and so that somehow generates correlation functions, right? Then, okay, but this still somehow has, I mean, this just has the standard correlation function. So first step one does is one goes to the Schwinger functional, right, which then generates us connected correlation functions. Okay, and so for instance, if I take the Schwinger functional, I take one functional derivative with respect to the source, right, that will generate me the expectation value of my field. Okay, so then to construct from that the effective action, right, this is the usual thing one does, right? One performs a Legendre transform, right? So instead of having a functional of these somehow fictitious sources, right, we now trade having these sources as our variables, as having the field as our variable, right? I mean, that's what the Legendre transformation does, and that's after all what we're interested in, right? We want to know what the field is, right? Okay, and so that is just given by the Legendre transform of the Schwinger function. Okay. Now, why is this nice? So the reason that this is now nice is that, okay, so now if I take a functional derivative of the Schwinger functional with respect to this scalar field, right, this gives me essentially the equation of motion of the scalar field. And so that is just like, so in a sense that's very similar to like an equilibrium, right? So Rob wants to compute his Polyakov loop, right? So what does he do? He extremizes the effective action, right, to get the correct value of his Polyakov loop at the end of the day. And so just like that, what I'm doing here is I take this effective action, right? I take a derivative with respect to the field, right? And that's what gives me the equation of motion then for the scalar. Okay? So that's going to be the quantum equation of motion, right? And so in a sense that's one-to-one analogous to somehow the classical equation of motion, right? So in the classical equation of motion we would have to extremize the action, and if we have a source present, then there would be a source appearing on the right-hand side here, right? But now the role is played here. So the role of the classical action in the quantum theory is played by this quantum effective action. Okay? And okay, so I mean, so to take this derivative is actually very simple, right? So you have, I mean, okay, so there's obviously you get this minus j on the other side, right? And then you have d phi dj, which cancels with the term coming from the derivative of the Schwinger functional with respect to phi. Okay. Now, what is the, okay, so then somehow the task becomes to now actually compute what this effective action would look like, right? Because that's somehow what gives us the equations of motions. And so the general form is kind of written over here. So if you set this 2-point source to 0 for the moment, and I need that a little later, then this quantum effective action will be given by the classical action. Then there's the one loop correction. That's again something that Rob also had in his analysis. And then in principle, the higher order terms here, so this I think is the 1pi effective action. They then contain somehow the loop diagrams, which are formulated in terms of having the scalar field, which is somehow self-consistently determined from the equations of motion. But sort of if we were to draw a diagram there, right? Let's draw some kind of diagram. So well, I guess the easiest we can draw is this tadpole kind of thing. Then what we would mean by this in the 1pi effective action is that somehow here the propagators that would appear in these diagrams would still be the free propagators in the presence of this classical background field. Okay? So now we may be tempted to think that this is somehow sufficient. However, it turns out it's actually not. So I mean, you can play this game, but as you saw, for example, in this example of the scalar field, right? Initially we had a somehow huge scalar field, but then we somehow had a very rapid growth of fluctuations going on. And so it turns out that if you work at this level, then essentially essentially this is contained in this thing here, right? Then essentially the fluctuations that enter in this 1pi effective action here, they're still treated at the level of being free field fluctuations, essentially. So I'm not taking into account that really the fluctuations that are present in my system are rapidly changing as a function of time, right? But I'm still propagating the fluctuations as if they were essentially free field fluctuations. And so that is essentially the reason that one has to go at least one step beyond that to also capture the evolution of these fluctuations self-consistent. Okay? So how can we go further? Well, we repeat the same trick, okay? So we just repeat the same trick, so we now perform a second Legendre transformation, right? With respect to this 2-point source that we had introduced, right? So previously, I think in the first lecture, there was a question, why did we introduce 2-point source? And well, precisely for that reason, that now we can perform the Legendre transformation also with respect to this 2 points. Okay, and so first we should look at what's the conjugate variable to that 2-point source, right? So if we take the Schwingarte function and we derive it with respect to this 2-point source, well then this will essentially, so if you go back to the construction here, right, and this will generate as a contour term ordered propagator of these 2 Heisenberg fields. And so what this comes out to be is just the contour propagator plus the field plus twice the field, plus the square of the field expectation value, or the field expectation value at 2 points. Okay. Now we can do a second Legendre transform, now with respect to that 2-point source, right? And so, okay, what that will do is it will now eliminate the dependence on the 2-point source, right? And instead give us the contour propagator as our variable. Okay? So just like in the ordinary 1-point Legendre transform, right? We trade the dependence on the source J for dependence on the field phi, right? Now we're trading the dependence on this 2-point source R for dependence on the somehow self-consistent propagator G. Okay, so we can do this. So we can do this other Legendre transform, right? So okay, we do this here, right? And then again from this effective action which depends on the field and the propagator, right? We can again derive equations of motion. So now, okay. So the equation of motion for the scalar field, in principle, just receives an additional contribution, right? But at the end of the day, we're anyway interested in somehow setting these sources to 0, right? So, okay. So it'll just be modified by somehow the effective action having a different form, right? Okay. But now, in addition to having an equation of motion for the 1-point function, so for the expectation value of our field, right? We now also get an equation of motion for the fluctuations in our system. And so this is important, right? Because the fluctuations in the system can change very dramatically as a function of time, right? And so if we have an equation of motion for this, right, we're able to account for this somehow self-consistently as we evolve the system of time over time, right? And so this is exactly like we did in the decay of the scalar particle, if you want so, right? We need to compute the fluctuations self-consistently here as well. Okay, so this has been very formal, right? So okay, so in principle this is then very nice, right? Now, okay, what's the challenge? Of course, is to be able to compute these effective actions, right? To be able to actually write down concrete equations of motion, not just this abstract blah here, right? We actually have to compute what these things are, right? And then write down explicit forms of equations of motion that we can actually solve, okay? And so you can work this out, what this is, right? So this is here in this CJT paper, for instance, rather cumbersome calculation, I would say, shows that, okay, so the general structure of this is something like this, okay? So you have, again, the classical action, which depends on your field, Now you have trace log of the inverse full propagator. You have another kind of a one-loop term here. And then you have what is called the two-particle irreducible effective action. So that's two-particle irreducible doesn't really matter so much at this stage what this really means. But so now the point is that in the diagrammatic expansions of this gamma 2 here, if I look at a diagram like this, right, then what will appear here is no longer just the free propagator in the presence of the background field, but all these corrections, so the corrections to the equations of motions, will be computed in terms of the somehow self-consistently determined propagator, so the self-consistent Green's functions, which are the solutions of the equations of motion. Okay? Okay. On the other hand, for instance, the vertices, right? So I mean, here we have a vertex here, right? So the vertices are still the bare vertices of the field theory, right? So this would just be the ordinary coupling constant lambda in our scale theory, but the fluctuations that run through the loop are now determined self-consistent. And so in principle, you could carry this to higher and higher orders, right? I mean, that's what's called NPI, so n-particle irreducible effective actions, right? You could now introduce a 3-point function source and so forth, and then do another the transform with respect to that. That would give you the 3-particle irreducible effective action, and you can carry this forth and forth in principle. Okay. Now, okay, so far I have some, yes?
What is the difference between G0 and G? I mean, you are saying that these are both propagators, right?
Yeah, so okay, yeah, very good question. So I mean, G0 inverse is just the term that appears essentially in the classical action, right? So if you write the quadratic part of the classical action, right, and this would be something x, y. I should write it as a function of, let's say, write it as a function of this var phi, right? Phi of x, and then you have G0 inverse of phi times phi of y, right? So this is just, I mean, this is something like box y plus m squared plus, let's put the delta function here, something like this, right? Plus phi squared of, what do we have here? Phi squared of y, I guess, over 2 lambda 2 here, something 3, I don't know, something like this, right? This is just a free inverse propagator, right? The thing that appears in the quadratic part of our action, right? Whereas G is actually what is up here, right? That's really the quantity that we're interested in, right? That's what's actually characterizing the correlation functions in our system. Yeah?
But both are time order product of those phi's, right? I mean,
no. So G0 inverse is not a time order product of any phi or something like this, right? That's just a mathematical object that appears in our classical action, right? And so usually what we would do in a standard perturbative expansion, we would say that, well, okay, time order products of our fields should to first order be approximated by essentially the inverse of this. Yeah. Yeah, so that would be saying, okay, I write my propagator as 1 over p squared plus m squared, right? Yeah. Here I'm saying, okay, no, this is not what you should do. You should actually solve an equation of motion for your propagator. Yeah? Because, I mean, part of the propagator, namely for instance, the statistical 2-point function characterizes the fluctuations in the system, and this can change as a function of time. Yeah? That's why you have to be careful and solve an equation of motion for this. Further questions? Okay, I don't see any, so let's carry on. So at this stage, this is somehow all very abstract. So let's actually just start to look what this actually looks like. Yeah. So to kind of just give you a little bit of a feeling of what these things look like. So I worked this out here for up to 2-loop order in the effective action. And so okay, so we have these equations of motion, right? You then have to calculate what is this gamma 2, and then okay, you take your derivatives, and that's how you get your equations of motion, right? And so the way that these turn out to look, so let's first look at somehow the equation of motion of, say, for example, this scalar field. And so as I said, right, I've truncated this here. I've truncated now the expansion of this. So I've truncated the expansion of the effective action at 2-loop order. Okay. So for the background field, and so this is now really an equation of motion for the expectation value of that field, right? So there's no longer the notion of having individual ensembles and statistical averaging over individual ensembles, but it's directly an equation of motion for the expectation value. What do we find? Okay, so I've sorted it such like this, that on the left-hand side we have essentially what is the free field equation of, or not the free field, I mean the classical field equation of motion, right? So here we have a part which just comes from the classical, which is derived from the classical action, but then this classical equation of motion now receives correction due to the fact that somehow the field can interact with say, for instance, with the fluctuations in the system. And so, okay, so you can look at these diagrams. So in the presence of a non-zero background field, right, you not only have this, so you have the bare vertex to which you can attach propagators, right, but you also can sort of attach a field insertion to this, right, and then you have sort of an effective 3-point vertex. And so that is actually what appears in somehow the first diagram. Okay, so that would be somehow the field now coupling to the fluctuations in the system. Okay, so but that's still a local term. So by local, I mean here that it's all the time and space arguments are evaluated as the same position as the field itself, right? And then on top of that, there are somehow these loop corrections, which essentially characterize us how, well, a field that was present at some space-time point y, right, could somehow go through this loop and then affect the evolution of the field at some different space-time x. And so, as I said, right, now all of these are expressed in terms of somehow the self-consistent propagators, right? So you have the actual statistical correlation function and the spectral functions appearing inside these loops. And so likewise, you can now go and look at, what you should do is you should calculate what is this two-particle irreducible effective action up to a given loop order, say, and then take functional derivatives with respect to the field and with respect to the propagator, right, to somehow have self-consistent equations of motion for the pair. And so like that, you then get equations of motion for the propagator, which again you can decompose them conveniently into this basis of, again, statistical and spectral 2-point correlation. So what do these equations of motions for these propagators look like? Well, what they look like is, okay, so here I've sort of separated the three parts. So this actually clarifies what this factor over there was, right? So this is just the free inverse propagator multiplying the, in this case, the statistical 2-point correlation function. So this is, if you want, free field evolution in the free fluctuation evolution in the presence of this background field, right? But then the point is that these fluctuations now can interact with each other, right? And so that is encapsulated in these other type of corrections, right? So the first one that appears is this kind of standard tadpole one, which again acts like adding to the effective mass of these particles that you have in there, right? But then you have the other ones, right? So that would be corresponding to this diagram, which, okay, so essentially what this describes is some kind of two-body scattering process here, or like a 1-to-2 scattering process in the presence of the scalar field. So you have scalar field insertions at 2 points, you have propagation in between, and so there are essentially two components to that. Okay, now so I just wanted to kind of say, and so these are really quantum equations of motions, which are now, okay, accurate up to a certain order in the coupling. Okay, so couple more comments for this. So what is some of the structure of this framework? So it's important, and I mentioned this earlier, but let me point this out again. It's important to say that these evolution equations that I had put down here, for instance, right? They're really evolution equations for expectation values of both the fields and the fluctuations, right? And so that's different. So that's different than say in the classical statistical approach that we had before. where we had an ensemble-based approach, right? So in the classical statistical approximation, we said that, well, okay, we have to somehow compute things as averages over multiple trajectories, right? And that's effectively what then somehow generates some of these loops that appear on the right-hand side. In contrast here, right, these equations of motions you only have to solve once to describe your systems because they're already equations of motions for expectation values. Now, the other thing one can say is that this expansion, of course, now includes both these classical as well as these quantum vertices, right? So we somehow haven't distinguished between the two, and in a sense you can see this here, right? Because somehow each of these diagrams contains both powers of S as well as powers of rho, right? Whereas in the classical statistical approximation, we would have always expanded F much larger than rho, right? And so we could kind of kick out a few terms over here, okay? Now, these things are also to some certain extent nasty beasts, and that's why okay, you may say this all sounds almost too good to be true, right? And yeah, the thing is these are also nasty beasts in the sense that their structure is very, very complicated, right? And so this is related to the fact that actually, if you look at what appears on the right-hand side, so you see this, I mean, perhaps the easiest way is to see this in these diagrams, right? So really what you're asking, I mean, what really appears on the right-hand side is somehow higher n-body correlations, right? But okay, so what you're saying, okay, when you have a self-consistent field and a self-consistent propagator, you're essentially still expanding around the Gaussian state. Yeah? Whereas everything that appears on the right-hand side is essentially non-Gaussianities, if you want. And so the way that these non-Gaussianities are built is they're built through the interaction of essentially Gaussian fields, and therefore they involve these memory integrals. So this is, in a sense, this is very similar to what you see when you say derive BBGKY hierarchy for classical particles, right? And you also have all these complicated things appearing on the right-hand side, which in principle characterize your multi-body correlation. And so to build actually these many-body correlations, they're built somehow dynamically during the time evolution, and so this is why you then have the appearance of these memory integrals, where now somehow to evolve your field forward in time, right? You not only need to know somehow the state of your system at a current time, but you also need to know its history to a certain extent, right? Because that's what determines the properties of non-Gaussian correlations at this at this stage, and so that's really why they are in that sense not that easy to use. I mean, if you were to now wanted to go ahead and actually solve these numerically, this is actually quite the task. I mean, this can be done, and there's some very interesting studies doing that. If you want to have a look at this, you could actually look at here, for instance, this nice lecture notes by Jürgen Berges. But it's certainly significantly more difficult than doing a classical field simulation or something. Nevertheless, this is a very powerful approach, and I've really, in a sense, not done justice to this here, because I mean, what I showed you was just for convenience and to somehow familiarize oneself with how does one actually get equations of motions for the quantum theory, right? I've just done the simplest expansion of this effective action to two-loop order, right? That's the dumbest thing you can do. That's the dumbest non-trivial thing to do. Now, where the real power of this actually derives from is that at least in some theories, you actually know how to sum quite a lot of diagrams, okay? And so particularly in scalar field theories, there are these very powerful non-perturbative expansion schemes which don't expand in the coupling constant, but they expand in the inverse of the number of field components. So you take, instead of having a single component scalar field, you take multi-component scalar fields, and then you can actually expand in the number of field components, and this is known, I think, how to do up to third order or so even. So this is really amazing, and by that you're actually able to really sum a lot of physical processes going on in the system, and you can really do amazing stuff with this. Now, another reason why I'm not going to dwell into too much detail for this is that, of course, okay, so as usual, right, I've taken somehow the easy route here and sort of worked this out for scalar field theory. If you want to do this for gauge theory, then this is certainly a lot of these things become become much more problematic, right? So first of all, okay, I mean, the approach is again explicitly somehow formulated in terms of correlation functions of the fields, right? So there are obvious issues of gauge invariance that you have to deal with these approaches. Another point is actually that in gauge theories, in fact, even if you just want to somehow describe what is usually considered as the leading order of the expansion within such an approach, then you have to deal with all these issues of having somehow soft regions and nearly collinear processes going on. Yeah? And so this is actually not sufficient. You need to at least go one order higher. You actually have to also construct self-consistent 3-point vertices in this framework. And this is really, I mean, this is really becomes very painful. So I put down a couple of references here which dealt with this in the context of gauge theory. So if you want to look at this, you can, but yeah. Which one?
The term in the classical equation of motion, the interaction term, the lambda phi squared term.
How do you mean? How do you deal with this?
Well, you cannot invert this propagator, right?
No. I mean, what you do is, right, I mean, so you have a box here, right? So what you do is so the way I've written this is formulated with an initial condition at a time which I set to 0, right? So at 0, you have to specify what is my field, what's the expectation value of my field, and essentially what is the expectation value of my statistical, so of my 2-point function, right? So of my statistical 2-point function, and the spectral function is fixed by equal time commutation relations. Yeah? And then, so this is dt squared plus gradient squared and so forth, right? And then you just start solving equations of motion, right? You really just solve them by forward integration in time. That's in principle what you're supposed to do. Yeah?
It's a nonlinear equation. Right?
It's a So you can, I mean, this is what I'm having in mind here, numerical integration of the nonlinear equation. I mean, that's something you can do, and that has been done. I mean, it has been done for the simple kind of truncation, but also has been done in somehow more elaborate truncations like this 1/n expansions, for instance. I mean, that's, I mean, getting an analytic answer to these difficult questions is, it would be awesome, but I think it's more or less hopeless, actually. Yeah. More questions? Okay, so good. So now, now we somehow derailed a little bit from our starting point, so to say, right? Because really what we wanted to have is somehow a simpler understanding of this non-thermal fixed point, right? And I introduced here this somewhat complicated framework, right? So let's try to do if we can somehow further simplify this. And so there is actually there's now a way to somehow get from these very nasty looking things and very complicated things that are going on actually to much simpler things like we may be familiar with, like kinetic theory. Okay, and this is the real reason. So the reason of going through this like this is this. Okay, I find this a relatively systematic approach to somehow derive kinetic equations in quantum field theory. And I also just wanted to give you a little bit of a feeling of what there is out there in terms of non-equilibrium. Okay, so these equations of motion, they're sort of a little bit nasty for two reasons. The one of them is somehow that we have these memory integrals, which really makes them a pain, right? But also they're to a certain extent, I mean, not really that efficient, because they really feature somehow two distinct time and length scales, time and length scales. And so this is something that can actually already be seen at just the example of taking, say, a spatially homogeneous free field, right? So if we take a free field theory, then in principle nothing should happen, right? I mean, it's just evolving free fields, so they should just wiggle and that's it. Okay, good. But now if we somehow calculate these complicated f's, right? We would still have to, in this case, there would be no memory integrals, right? But we would still have to solve this equation of motion somehow for all different times and space arguments and so forth. And life is very, very complicated. Okay. Now, okay, but if we actually work this out, right? Then we can work this out, so we have some initial occupancy in momentum space, right? And so what we will see is that actually in the free theory, this function depends on the time only through the difference between the two times. So it's somehow rapidly oscillating in the difference time, but there's no dependence on well, if you want, so the center of mass time, which is the average of these two time arguments. And so that's kind of characterizing where I am on average, whereas the other thing is just measuring the correlation function between two different points, somehow keeping the average point where I measure it fixed. And so likewise, this is true for the spectral function also, right? Where again, so instead of a cosine, you have some sinusoidal oscillations here. So the situation is somehow that we have these very rapid oscillations typically in this difference coordinates, which I'm going to call S in the following, okay? But since the system is somehow, in this case, is homogeneous and the properties of the scalar theory don't change as a function of time, right? There's essentially, in this case, no dependence at all on this central coordinate, which is somehow the sum of these two, okay? Now, if we turn on sort of weak interactions, right, well, what do we expect to happen? Well, I mean, these rapid oscillations are somehow not going to go away, right? There's still going to be rapid oscillations, right? But in addition, what will happen is there will be somehow slow changes now as a function of this time. And so we kind of want to, so what we is, I mean, so typically what we should expect is that, somehow gradients with respect, so if we now write, so we invert this transformation if you want, so and write x and y in terms of s and x, right? So then typically the gradients with respect to this somehow central term will be much smaller compared to gradients with respect to this difference term. And so to somehow take into account these fast oscillations, I mean, if you have a function which just oscillates all the time, right, then you probably don't want to deal with this in real space, but you rather want to deal with this in Fourier space. And so it becomes then convenient to introduce these objects which are called Wigner transforms of these two-point correlation functions. And so one, so what one does is one goes from having this formulation in two spatial variables to having one spatial and one momentum variable here, simply by doing a Fourier transform, which then somehow contain both time / position and frequency and momentum information. And so what one can do then further is one can now, since we're somehow expecting the system to evolve slowly in time, right, one can then further perform an expansion in gradients. And so actually the expansion goes in gradients of x multiplying gradients with respect to this momentum variable. That's somehow the structure of the expansion, what that one has to do here. And so doing that expansion and somehow keeping that to leading order, one then gets from the equations of motions that I showed, to equations of motion which look something like this. So they now characterize, so let's look at the first one, right? So they characterize the change in, say, time, so central time of the two-point correlation functions, in terms of various terms, which are again related to these loops appearing on the right-hand side. But now what is happening is that, so these expressions are given down here, that somehow each of these loops is now sort of instantaneously determined in space and time by the properties of the fluctuations at that space-time point and the properties of the spectral function at these space-time dots. So they now, upon performing a gradient expansion, in a sense this is not surprising, right? You perform gradient expansion somehow to leading order, then things look local. So you now get local interaction terms in space and time. And so this is now almost actually already at the level of kinetic theory, which, kinetic theory has a very similar structure, except that some of the objects that are appearing here are not yet quite the ones we're used to in kinetic theory, okay? And so one of the reasons in particular that this is not quite kinetic theory, so I think this is usually called off-shell transport, or I think is this what one calls Kalanov-Baum equations, I guess, right? Okay, anyway, so this is already, in essence, this is already very similar to kinetic theory, except that in kinetic theory, we actually do one further approximation, which we're going to do in a second, which is an approximation in the spectral function. And so in this case, these equations of motions here, these off-shell transport equations, well, they still include off-shell processes, which means that, well, okay, the spectral function is not just the spectral function of a free theory, but it's essentially still something that's self-consistently determined within this approach. I didn't write down the equation here, but it's easy to work out as well. It's basically the usual correction by the self-energy that one has to take into account. Okay, so now getting to kinetic theory, there's, as I said, there's sort of the last step involved, right? And so the last step that's involved now is if you somehow look at, okay, what is characterizing the changes in time of somehow our statistical fluctuations, right? And you see that is, well, that essentially this is already proportional to lambda squared here, whereas all the corrections to the spectral function that we will encounter will also come with powers of the coupling. So if we're only interested in somehow the leading order behavior in the coupling, we can go one step further and actually just plug in the free spectral functions, right? Because all corrections are going to be higher orders in the coupling. And so turns out if we do that, right? So if we do that and somehow plug in free spectral function there and define an out of equilibrium occupation number by the relation of the statistical correlation function with the spectral function, we can first integrate the left-hand side here. So we integrate this over the positive frequency modes. So, okay, you can integrate this, okay, so you get P0, okay, then the spectral function gives you an inverse P0, so you just get ETN, right? Then you get the usual gradient term, and you get whatever is left on the right-hand side, right? And so what's left on the right-hand side is the collision integral, right? And so this then really somehow takes the standard form of a kinetic equation. Okay, so now, okay, so I should note, okay, so this actually also took up a lot more time than I thought it would take up. So I might have to speed up a little bit here to get in what I wanted to get in, right? Okay, so this was somehow a rather lengthy derivation, but I just wanted to get you a feeling for somehow how one can actually get to these kind of kinetic equations. But if essentially you know how to get there, right, then there's also more efficient ways to somehow just calculate the matrix elements involved there. I mean, you can perform these expansions in various different orders, right? For instance, you could first set all your stuff on shell and then just calculate the scattering matrix elements, and that's typically a much more direct approach to get there, right? This is just, I find this rather systematic, and it somehow makes it apparent what are actually the levels of approximations that are being involved. Okay, so what we learn from this is we actually learn, okay, I mean, why do we take all these steps? Well, because we now learn, okay, what are actually the assumptions that go in, right? Okay, so what have we done to get to kinetic theory? Well, okay, we have on the one hand done a gradient expansion, so we've expanded somehow, if you want, so our distribution in gradient, or the corrections to the equation of motion of our distribution in gradients with respect to space, time, and momenta, right? But I mean, for the phenomena that we want to discuss, right, things are somehow evolving slowly as a function of time, so that shouldn't be much of an issue, right? The real place where we have done an expansion is we have actually done the perturbative expansion. And so the perturbative expansion, what does it really mean in this context? Well, it's on the one hand an expansion in the coupling constant, so that we need, for instance, to actually be able that we can to actually say that we can approximate our spectral functions by having somehow well-defined quasi-particles, just a delta peak essentially. But then if you think about it, right? So really, when you're now starting to draw these diagrams, right? Then each time you somehow put a vertex, right? You also have to attach a propagator to it, right? And so the propagator will contain the fluctuations in the system. So we're not only, and so the fluctuations in the system are proportional to the occupation number, right? So we're really not only expanding in the coupling, but we are also expanding in the coupling times the occupation number, right? Because that's really what enters somehow, what would enter in higher order processes, right? And so that's, I mean, intuitively from the picture of scattering that goes in the Boltzmann equation, that's also clear, right? If you had a, whatever, 17 to 15 process or something like this, right? Then, well, the 17 to 15 process would have 17 powers, would have to, 17 particles would have to meet for this to happen, right? So that would be proportional to the 17th power of the single particle distribution n. So kinetic theory is, in that sense, a combined expansion in the small coupling, but also small coupling times small occupants. Now, if we compare this with the classical statistical approximation, that's non-perturbative in the coupling, but it's essentially an expansion in the inverse occupancy to leading order. So that requires that our occupancy is much larger than 1. And so you can now somehow compare these two ranges, or the range of validity of these two approaches. And so what you find is that if you have a weakly coupled system, so system which is much, where the coupling is much less than 1, there's actually, I mean, there's a well-separated regime between where occupancies are of order 1 and where occupancies are of order 1 over lambda, right? And so while the classical statistical approach is somehow valid in the regime of large occupancies, the kinetic theory is valid in the regime of small occupancies, up to somewhere well below this non-perturbative scale. And so in particular, you find that there's somehow this overlap in the range of validity, and that's actually exactly the regime where, for instance, these non-thermal fixed points. And so the beauty of this is now that, okay, we can now use this tool that we now understand where it comes from to somehow try and better understand what's going on in the vicinity of these non-thermal fixed points. Okay, questions?
You can also write down 2pi versions of classical statistical.
Yes.
So how they,
Yeah, so I alluded to this actually here. I tried to allude to this. So basically what would happen is you would always, I mean, you would miss powers of the spectral function over the statistical two-point correlation function. That's in essence what happens.
So you should not allow this spectral function inside.
Well, I mean, actually what happens, well, let me carry on. You'll see exactly where it comes. Okay.
Just wanted to say, in this way, it is easy to see the statement that you just made that the overlap. I mean, you had a proof of getting kinetic theory from the 2pi, and there is also a well-defined way to take the classical statistical limit of 2pi. Mm-hmm. So in this way, you can prove that these two are exactly the same, or these two.
I mean, if you do classical 2pi, right, then I mean, if you do classical 2pi, then you basically have to cut this here too, right? Because you cannot penetrate into the non-perturbative regime unless you know how to resum essentially everything, okay? Yeah. But if you do if you just do statistical field evolution like we did before, right, then you're resumming at least all the classical things, right? And then thereby you push into this non-perturbative regime as well.
My statement is that in the regime where they are valid together.
Yeah. Yeah, you can also take the classical, and this is actually games that people have played, right? So they have, I mean, people have looked at sort of the classical version of 2pi and the quantum version of 2pi and compared them, you know, in the regime where essentially you can do this at the level of kinetic theory also, right? You take the classical limit of kinetic theory and you take include the quantum version of kinetic theory and compare them in the regime where things should be classical, and surprise, surprise, you find that they're classical, right?
I'm just asking, is this formal proof, or I mean, this is what people find in? I mean, this is just an argument where it works in practice, or one can actually.
No, I mean, this is well. I mean, look, right? I mean, you have to solve the equation and check, right? I mean, you solve them numerically, you check what's the effect. That's the level you can do. I mean, on the fourth level, you can say, okay, these are the expansion parameters, so that's what you expect, right? But then, I mean, that's anyway how I would always check, right? I mean, you have to look what's your correction, you have to calculate it, and then you have to see, okay, is it big or is it small, right? Okay. More questions? Okay, I don't see any. Okay, so then let's try to use this little tool, this new tool here, right, to somehow try and understand these interesting non-equilibrium phenomena that we observe in this weakly coupled classical regime, let's say, of the theory. And so now I'm actually gonna switch to do this not in a scalar theory anymore, because actually, funnily enough, turns out to be this is a little bit more tricky in the scalar theory. And so I'd rather like to do this for a non-abelian plasma. So let me briefly introduce you, okay, somehow what are the kinetic processes in the non-abelian plasma. And I'm gonna be very brief here because next week there's gonna be a full set of lectures on this, okay? So roughly speaking, the structure of the kinetic theory for non-abelian plasmas at leading order takes the following form, and can be written in the form of a standard Boltzmann equation. It should be understood that this is really only valid to describe somehow hard excitations in the system, so system excitations which are well above the Debye screening scale. Okay? So for these kind of excitations, there's essentially two types of processes that you have to consider. There's on the one hand elastic scattering processes of gluons, say. So let's just say we're only dealing with gluons here. Yeah? And on the other hand, there are so-called inelastic or radiative processes that go in. Yeah? Okay, so let's first talk about the elastic processes. And so in principle, the elastic processes, it's convenient to somehow to somehow separate into small and large processes with small and large momentum transfer. Why is this convenient? Well, processes with large momentum transfer, this essentially happens when sort of two gluons meet close together, right? And these are things you can actually calculate perturbatively, right? Whereas the small momentum transfer processes, they come from sort of a gluon being here, feeling the field from another gluon that's very far away, yeah? And so if you actually want to calculate them, you somehow have to take into account how the environment essentially affects the long-range properties of this field, and you have to take into account screening phenomena and so forth. Yeah? And so that's why it's oftentimes a good idea to essentially separate them into sort of small-angle diffusive type processes and really hard scatterings between gluons inside the medium. And so these you can calculate entirely perturbatively, essentially, and for these you have to somehow take into account medium modifications of the color fields inside the medium. Okay, so now, so what's the physics of these? So small angle scatterings turn out to be very frequent, right? So basically because you still have somehow long range fields and you can kind of feel the field from a lot of particles around you, right? But okay, of course, if you have a scattering with a small momentum transfer, this also has a very small effect on you, okay? And so it turns out if you somehow consider a typical hard particle in your system, then in terms of changing its momenta, actually both processes are somehow parametrically equally important. So they essentially have the same kind of effect on the momentum of a hard particle. Then on top of that, there are these inelastic scattering processes. So what do I mean by this? Well, okay, I mean, we're dealing with charged particles here, right, which are getting kicks, right? And so when a charged particle gets a kick, that means it's accelerated, so it can emit or absorb radiation. And okay, there's somehow further complication here, and Edmond will probably discuss this in great depth today, is that actually, since we have these very frequent small angle scatterings in the medium going on, one thing that can happen is that somehow it becomes important to consider essentially coherence effects between different possible emissions, and so thereby you have to then distinguish regimes where essentially radiation is triggered independently from each scattering center that you go through, or where you really have to care about somehow multiple scattering centers acting coherently for the emission of radiation. And so that characterizes essentially two different types of regimes, namely the one which is the single scattering regime, which is the Bethe-Heitler regime, and the other one which is called the LPM or Landau-Pomeranchuk-Migdal regime. Now, generally, now, what we want to know is how important are these compared to, say, these elastic processes. And so generally what one should say is that the relative importance of these processes depends, again, on the momentum scale of the particles you're looking at. If you look at very highly energetic particles like jets, right, then, I mean, already our intuition tells us that they're somehow dominated by their evolution is dominated by radiative processes in the medium. And so indeed that turns out to be true, simply because, okay, I mean, if you give a large excitation a small kick, it's not going to do much. It's much easier for it to somehow radiate some stuff to, say, lower its energy. But so if you look at some of the typical scales of the medium, so when I talk about the scale Q here, right, you should have in mind somehow, say a particle which sits at the front of the self-similar cascade, then it's actually equal. Then these inelastic processes are equally important as these elastic processes. And so one thing that this means is that somehow, we can efficiently essentially deplete or either deplete or increase particle number at the system at the same rate that we can somehow change momenta in the system in a non-abelian relation. Okay, so what we want to do now is we want to now somehow study this phenomenon of these non-thermal fixed points, which are these self-similar scaling solutions, based on these kinetic equations that we have, right? And so, well, the natural thing to do there is, right, I mean, knowing that it seems like there should be solutions of this form, right? Okay, well, we can take this as somehow our ansatz and simply plug this into the Boltzmann equation and see what comes out of this. And so you can play this game, right? So if you now somehow search for this type of solutions, right, then basically what you have to do is you have to, well, plug this into the left-hand side and you have to plug this to the right-hand side and you have to see what you learn from that. Right? So already plugging this into the left-hand side actually already reveals somehow the structure of what is going to happen here, right? So then I plug this into the left-hand side, so I have to This is my ansatz, right? I have to take a time derivative, right? Okay, so I have to take a time derivative with respect to this term. This generates the first term, right? But I also have to take derivative with respect to time of this rescaling of the momentum argument, which is going to generate the second term. But now the interesting thing that happens is somehow that once I do this, I get essentially a factorization into two kinds of components. The one is an overall evolution of this scale factor, which goes with a certain power of this exponent, here gamma minus 1. And the other one is somehow entirely characterizing the momentum dependence in terms of now a rescaled momentum, which is this p twiddle. But so that's, so once you call this p twiddle, then this is essentially independent of time. And so this is, this is already quite remarkable, right? That, just plugging something like this in, right? You have essentially factorized the time and momentum dependence of this collision. Now, okay, that's just the left-hand side. That's okay. That's kind of trivial, right? Really, the question is what's going to go on with the processes on the right-hand side. And so, in principle, you have to consider all the different processes that enter on the right-hand side, right? So, small angle elastic scattering, large angle elastic scattering, and inelastic processes. And this has been done actually. So, throughout the series of papers. And so, actually, if you do this, that essentially what you find is that at the end of the day, they all behave in very much the same way, and so I'm not going to show you all of them. I'm just going to show you, for example, how this works for this large angle elastic scattering process, because this is also kind of, this analysis that I'm going to show you is actually very standard analysis in the context of what is called wave turbulence. You will find this, for instance, in chapter 9 of Nazarenko's book on wave turbulence. And so somehow, best way to see this, I would say, is at the example of this large angle elastic scattering process. Okay, so let's try and do that. So we'll only consider these large angles, the scatterings with elastic scattering with large momentum transfer here. And so the structure of the collision integral for this is given by this. There's a matrix element here, which the details of which are essentially irrelevant to us for the moment. Okay, they are energy momentum conserving vertices, right? And then we have these standard factors for the scatterings, right? So, okay, so here particles Q and K can go to produce P and L, right? And there's the usual Bose stimulation in the final state, right? And then vice versa, there's the loss term here, which is characterizing the inverse process, so losing that particle with momentum P to scatter into another state. Now, what we already know is that these non-thermal fixed points, right, they're things which occur in the high occupancy regime, right? So they only occur in the regime where somehow we have this large phase space occupancy, and that's actually essential for the analysis that I'm going to show. And so in the high occupancy regime, right, we should be able to expand essentially these 1 plus f terms, right, only keeping leading powers of f, okay? Now, while at the first sight you may be tempted to say, okay, well, there's f to the 4 terms here, right? Turns out that f to the 4 cancels exactly between this process and the inverse process, and so the leading terms that survive are actually these f cubed terms, which I've written over there. And so, by the way, this goes back to your question. If you were to directly derive the Boltzmann equation in the classical field theory, that's actually the answer you would get would be actually exactly this here. So here you can start with the quantum theory and then take the high occupancy limit, or if you start directly in the classical theory, that's actually the Boltzmann equation you would get for the classical theory. Okay. So now the goal is, in this case, is again, so on the left-hand side of the equation, we had this very nice factorization of the time and momentum dependencies. And so the question is whether we can find something like this also for the interactions that are going on in the system, right? And so, okay, so we want to see if this is happening. Well, what can we do? Well, certainly what we can do is we can plug in this ansatz into now this collision in, right? So taking first the classical limit and plugging in this ansatz, right? This factor I can simply pull out, right? And but then I end up now with having this distribution, right? Evaluated at this somehow funny scaled arguments. Okay. Now then you play a couple of tricks, right? So I'm going to be rather brief here, but you can, if you want, you can work this out in the set. Okay. So now basically what you do is you do a few scaling transformations here. And essentially what you want to do is, if you see this here, you want to do a scaling transformation of this integral measure, which is basically what is written up here, to then essentially get rid of this t to the alpha factors everywhere. Okay, so you can do this, right? Okay, so basically what you do is you do a bunch of change of variables, right? Then, okay, then there will be scaled arguments appearing in your matrix element. But then it turns out that since the theory is scale invariant at the leading perturbative level, this matrix element is actually also scale invariant, and you can again pull out these prefactors of time. So at the end of the day, right, so you have to keep track of the factors that are here inside the energy momentum conserving delta functions, you have to keep track of the factors that appear somehow in the dispersion relations, and you have to keep track of all the factors that appear inside your actual scattering matrix element, right? But what you find at the end of the day is, just comparing the first line to the second line, is that you can write this as a measure for these rescaled quantities, simply pulling out again an overall scale factor at time. And so the property that this relies on really is somehow having scale invariant dispersions, having scale invariant matrix elements. Okay, that's the only two properties you use actually to do this, and I mean I wrote here in detail what the steps are. Okay, now once you have this, right, you can go back to continue somehow this analysis of the collision integral. And so now using this rescaling of the measure, right, you can rewrite this in this form, where now basically all the arguments have this rescaling. And so this is exactly of the form as you had the original collision kernel, except now all the distributions that appear on the right-hand side no longer involve somehow your time-dependent, your time and momentum-dependent distribution, but they only involve somehow the stationary fixed point distribution here, right? Which is just the stationary scaling function. And so what you find is again that up to an overall prefactor, which is exactly this scaling of time here, this expression is just the original collision integral with f replaced by the stationary f and p replaced by t to the minus alpha p. And so the same kind of scaling phenomenon that or the same kind of factorization, let's call it, that you had on the left-hand side of the Boltzmann equation also appears on the right-hand side of the Boltzmann equation. Then there's an overall scale factor with time, and then the entire momentum dependence of this is encoded, and the momentum dependence is encoded here, but only depends on somehow the scaling function of your fixed point distribution. And so this is really, so now you have to somehow put the pieces together. So this is really, what happens is really somehow amazing, right? You start with this complicated Boltzmann equation, right? Complicated integral differential equation. But then plugging in this kind of an ansatz, right? You have this factorization happening on both sides, right? And so for this equation to be valid at all times, right? Essentially what has to happen is exactly two things, right? On the one hand, these yellow things which encode the momentum dependence have to match, right? But on the other hand, also the time dependence on the both sides has to match, right? And so what you find is that this rather complicated equation actually decomposes into two conditions. One is this very, very simple scaling relation here, right? Which is comes from matching the time dependence on the left and right hand side, right? And the other one is this extremely nasty integral differential equation, right? Which determines the spectral shape of this fixed point distribution, but no longer depends on time, right? So that just determines somehow the spectral shape of this stationary distribution. Now, this is already very nice, right? Because somehow this seems to give us a constraint on somehow what is the allowed values of the scaling exponents, right? And if you remember, right, the scaling exponents are really what determine somehow the dynamics of this cascade, right? So for instance, the characteristic momentum grows as what? T to the gamma, I think? T to the gamma, right? Grows as a power of T to the gamma, right? So that's really what's governing the speed of the evolution, right? However, at this point, right, I have two exponents and I have only one scaling relation, right? So it's somehow not enough to determine this fully, right? However, it turns out that actually the second constraint is extremely simple, right? And as I said very early on, or repeated multiple times, right? Really what this what the thermalization process does is the transport of energy, right, across a large separation of scales. Okay, one obvious condition on this process is that somehow the energy is conserved throughout this evolution, right? And so, okay, you can again evaluate the energy, right? So energy is, well, the energy of each particle times the distribution of particles integrated over momentum, right? So you can again plug in your thing here, right? You find actually a second scaling relation, which simply comes from the conservation law. And so indeed, right, if you then go and combine these two constraints that you have, namely on the one hand, the scaling relation that comes from the conservation laws, along with the scaling relation that comes from the dynamics of the system, right? You can work this out, right? You obtain these scaling exponents, and if you remember back, right, these were exactly the same ones as we observed in these simulations, right? And so, in that sense, somehow combining these different techniques is extremely powerful, right? Because on the one hand, these classical simulations, they can really be used to somehow give you a first principle answer, at least in this high occupancy regime, right? But you can then go and do these relatively simple analyses, right? And try to figure out, what are really the processes that are contributing. Now there's another nice consequence of this, right? And so this is actually the deeper reason why I kind of walked you a little bit through this analysis, right? I mean, you can say, why is this guy standing here showing me here this incredibly technical stuff, right? Point is, doing this incredibly technical stuff, you actually learn something, right? And so namely what you learn is that actually, okay, so you can do the same thing for scalars, by the way, also works, right? And then you have to actually use exactly the kinetic matrix element we derived. Okay, so what this analysis shows you really what properties of the theory you've actually used now to somehow determine this scaling exponent, right? And so really it only depends, somehow what determines this exponents at the end of the day are really only very few things. So namely, so if you go back, right, so you kind of look at where you collected these exponents, right? On the one hand, okay, so you had 3 appearances of the single particle distribution that gave you a factor of 3 here, so clearly depends somehow on the order of the process that you're considering, right? If you had 5 particles scattering with each other, there would be 5 powers of F here, okay? So it depends on the order of the process. It also depends, so that's essentially the part we skipped a little bit, but it also depends on somehow the scaling properties of these matrix elements. It will depend on the scaling properties of the dispersion, right? And so since we're performing integrals and we're also doing transformations with integrals, will also depend on say, for instance, the dimensionality of the space that we're looking at. I mean, with gauge series, we only want to look at 3 dimensions here anyway, but you could do scalars in different dimensions, for instance, also. So let's see if I listed them all. So exactly, right? So what you find at the end of the day is that actually what these things depend on, they only depend on the order of the n-body process, the scaling dimension of the associated matrix element, the dimensionality of the system, and the dispersion relation. Now that seems like a lot of things, right? But if you think about it, that's actually very, very few things, right? In particular, they don't depend on any of the microscopic parameters of the theory. They, for instance, don't depend on the number of colors. They don't depend actually on the detailed size of the coupling strings, right? As long as somehow the coupling is sufficiently weak to actually warrant the description that we're interested in. And so, since we have this independence of these microscopic quantities, right? Really, what that means is that gives rise to a notion of universality. So, different theories, which are somehow different, characterized by somehow, say, a different number of colors or different coupling strings or whatever, right? They can exhibit the same scaling properties far from equilibrium, irrespective of what that microscopic parameters are, right? And so, for instance, for SUN, so here's kind of a collection, right, of 2 of these far from equilibrium universality classes. So on the one hand, there are, for instance, SUNC Young-Mills theories in 3 dimensions in this high occupancy regime, right? They have these kind of exponents, and for instance, you can work this out for the scalar, so I showed this more or less for the single component scalar. The same goes true actually for n-component scalar theories, and there you get a different set of scaling exponents. And so this is really very nice, right? And so you can, okay, so now somehow doing this essentially perturbative analysis comes this insight that these things should be independent, right? But then to somehow use the full interplay of these methods, you can now go back and somehow actually look, for instance, at simulations again, right? And so we actually did some simulations to somehow explicitly verify this kind of thing. So now here, what I'm showing here is now an example comparing SU2 and SU3 Young-Mills theory, for instance. And so, again, so this is now looking at these kind of moments of the phase space distribution, so looking at the hard sector over here. And so I think, so what is it? Red is SU2, blue is SU3, okay, right? And so, okay, the bottom line is, right, okay, so you find scaling in both cases, right? And actually, if you somehow scale time by the number of colors here, this also depends on how you set up the initial conditions, by the way, and you can really find that actually you can map them exactly on top of each other, right? In particular, you can almost done. In particular, you can really extract these scaling exponents with statistical uncertainties, right? And so you find, okay, within the uncertainties, they're really exactly the same in these two theories, right? And they actually agree very nicely with this perturbative analysis. What's perhaps somehow a little bit more non-trivial, you can also somehow try to, I mean, this was all terribly perturbative physics, right? And really looking at somehow properties of hard excitations in the system, which in a dilute system eventually should be, or in a not non-perturbatively high occupancy regime eventually should be weakly coupled somehow. Now, you can also do this, you can also look at somehow softer properties of the system. So here looking at really physics of the soft sector. So what we looked at here, for instance, is properties of Wilson loops, so the trace of large Wilson loops, spatial Wilson loops. And so this is basically characterizing the long distance properties of magnetic fields in your system, which you believe to be actually very complicated at the end of the day. And so basically what you find is, okay, there's some kind of short distance behavior, and eventually this seems to settle on some kind of area law. So this is here plotted as a function of the area of the loop divided by the number of colors in the space. And so again, you can do this within the two theories. I don't know, so there's open points here in whatever triangles or something like this, which are SU2 and SU3, right? And so again, you actually see essentially no difference between the two theories. In particular, again, comparing the measurements at different times. You also here have a self-similar behavior of this Wilson loops. Now, in this case, I must say I don't have a particularly simple answer for exactly a particular simple derivation of this of what these exponents are, right, and why they should be the same. But it's very interesting to see that actually somehow this concept of universality far from equilibrium seems to carry over not only to having some of these terribly perturbative things, but also to having really interesting and essentially non-perturbative properties of the theory here as well. Can I get like 3 more minutes?
Yeah, sure.
Is that fine? Okay, good. Okay, so what do I have here now? Okay, so I wanted to briefly discuss. So this was essentially a question that also we started to discuss yesterday. Now, what does all of this now mean in the context of thermalization? Right? So the generic behavior that we have is that, okay, so we start from these initial states, which are highly occupied and far from equilibrium, right? And then generically what we find is this approach to a non-thermal fixed point, right? Where we have this self-similar scaling problem. However, what our analysis, now our kinetic analysis also clearly revealed, right, is that somehow the stability of these non-thermal fixed points, right, it really requires that we remain at high occupancy, right? Because otherwise I couldn't do this step where I threw out 1 compared to F. Okay? That was essential to actually having scaling properties of this thing, and so that's essentially for this cascade to continue. Now, of course, what happens is as this cascade runs out, right, the phase space occupancy drops, and at some point I can no longer do that, right? At some point this is just simply no longer warranted, the occupancies get small, right? And okay, that generically happens before the system thermalizes, right? I mean, in thermal equilibrium, the occupancy of Hartmut is 1, okay? So what one has is one actually has a breakdown of this classical statistical approximation before the system thermalizes, and so I can never use it to really study thermalization in the quantum sense, but I can use it to study some of these interesting, if you want to, transport phenomena occur. So as that happens, of course, the system will then also depart from the non-thermal fixed point, because the non-thermal fixed point is really only stable, I mean, at least the one I discussed here is really only stable in this classical regime, so under classical evolution, yeah? And so essentially what happens when the system becomes dilute is you have a departure from the non-thermal fixed point and you have an approach to the equilibrium. And so you can work out, I mean, since until that point you have self-similar evolution, you can work out somehow what are the time scales on which this happens. And so if you start with some initial phase space occupancy, which are called F0, up to some scale Q, right? Then the scale for this is basically given by this. And so it turns out that this scale actually coincides with the standard, so in this case, with the standard equilibrium relaxation, right, which is 1 over alpha squared t in this case. So basically somehow what this means is that parametrically at least the whole process of transporting energy from this low scales to these high scales will take the same amount of time as subsequently the system relaxing really towards equilibrium once this cascading process has ended. And so this is my last slide, right? So what that really means is that in general, to somehow describe thermalization process of a system, even if it's initially highly occupied, right? Really what we're gonna need is somehow a combination of different methods, right? Because the classical statistical approximation doesn't bring us to equilibrium, right? Can get us close potentially, but also that's not always the case, right? And so we generally have to somehow combine different non-equilibrium methods to actually study even the thermalization of a weakly coupled system. And so in particular, that's in fact exactly also what we do when we want to study somehow thermalization processes, say in heavy ion collisions or so, and I believe that Alexei Kukla will talk about this next week quite a bit. So for instance, when we study thermalization in a heavy ion collision in the weak coupling limit, we do exactly that, right? So we start somehow with a description of colliding nuclei in the color glass condensate framework, which then produce very strong color fields in the early stages that we use to describe using classical statistical techniques, before eventually the system somehow becomes dilute. That's when we pass it to a kinetic description, right? And so it turns out then that kinetic description is eventually able to describe thermalization of the system, or approach to hydrodynamics, maybe I should say rather, hydrodynamization, and then we pass it to a hydrodynamic description. And so this is really, I mean, this was something I was mentioning very early on, right? So typically to study somehow these complex phenomena, right, we need a combination of methods. And so this is true even if you're working somehow at very weak coupling, right? You really need for such a complex system, you need a combination of non-equilibrium methods to really somehow describe all the processes that go on from particle production all the way to where you actually form fluid-like plasma. Okay, thanks.
Questions?
I don't understand why you call this non-thermal fixed point is a non-perturbative result, because what's crucial to your argument is that the matrix elements have some scaling properties. So that's typically true at the leading order tree level. And if you now consider higher lambda corrections, they should be somehow suppressed dynamically.
Yeah, maybe I wasn't precise enough here. So I mean, clearly this scaling in the ultraviolet is terribly perturbative, right? All I'm saying is that here I'm actually probing behavior of large area Wilson loops, right? And I mean that's complicated. I mean that's a very complicated phenomenon, right? I mean that sits somewhere deep in the infrared, right? So that's infrared physics in a sense. That's why I'm calling it non-perturbative, right? Because infrared physics is necessarily always described by somehow non-linear field dynamics. Right?
Yeah, but
in that sense, it's not perturbative. Yeah?
But still, it is weak coupling and classical, because otherwise you will not have the scaling properties.
Yeah, I mean it's still weak coupling and classical, but I mean so these scaling properties. Look, when I saw this, I was very surprised actually, and I didn't expect to see this, right? I always thought, okay, this is something that's indeed, right? That's somehow very weakly coupled, very perturbative phenomenon, and so forth, right? The fact that you see something like this in the infrared is truly remarkable. And in fact, there's other cases also, for instance, in scalar theories where you have very interesting phenomena going on in the infrared. So yesterday I briefly showed this example of Bose condensation, right? So there again, this is also characterized by self-similar cascades, and there's sort of competing pictures how you can understand these things in terms of either defect ordering kinetics or also resummed quasi-particle descriptions. So, I mean, I'm not claiming this, so there's definitely interesting things going on. I'm not, but there's no somehow settled understanding of really what is happening there.
My question is related to Ayan's question, whether this scaling exponents that you derived, the scaling exponents, that does not depend what is your in your theory, like whether it is scalar or SUN.
No. Okay, sorry.
Because the way you derived it is just Boltzmann equation.
Yes, but of course the Boltzmann equation will look different, right, for a scalar field theory as opposed to a gauge theory, right? So as I said, I mean, so I talked a little bit about, the kinetic theory for the gauge theory, right? We have these elastic and inelastic processes. Turns out what's driving the evolution in the scalar is this interaction with the condensate. So perhaps an easier way, instead of looking at this equation here, right, is to briefly draw this on the blackboard. So the kind of scattering process that dominates this in the scalar field theory is actually this effective 1-to-2 interaction, which is mediated by the condensate. So it's a scattering process like this, and the other way around, right? Whereas in the gauge theory, you basically, you have elastic scattering. Let me just denote this by this, and you also have radiative processes, and you actually need both of them at the same time to realize this kind of scaling. So the processes are very different, right? I mean, they have, for instance, different scaling dimensions of the matrix elements and so forth. As you can in principle see here, right? I mean, this looks very, I didn't write down the matrix element for the gauge theory, but this looks different, right, than the other one. So therefore, see here, for instance, you get a different scaling relation, right? And you also get different scaling exponents, right? So for the scalar, for the gauge theory, you get these guys, right? This is what you get for ON symmetric scalars. Nevertheless, these are a little bit, okay, this is somehow, at least this ultraviolet scaling is terribly perturbative physics somehow, right? So in that sense, it's a little bit like mean field critical exponents. So you have very, very large universality classes, so to speak.
Any more questions?
Do you have a similar scaling fixed point for electromagnetic plasma?
For what?
Electromagnetic plasma.
I'm not aware of that, actually. I'm not aware of that. So, I don't think anybody has looked at it in this regime, right? What is trivial? Yeah, but you'd always have to go through fermions, right? That's the point, right? Unless you want to add some kind of photon self-coupling, right? Yeah. That's primarily the reason that I don't know what this. So certainly, so what I can say, and this is something we looked at, right? So I think I was visiting Maryland, right? And Paulo Bidaco, we got really excited about this too, right? And so we looked at whether you can get this for just say like a Maxwell gas or something like this. And so it turns out that, for instance, if you have 2-to-2 interactions in the So how was this? If you have 2-to-2 interactions but in the quantum regime, this actually does not happen. And the reason this does not happen is that essentially it's very hard to put the system actually far away from equilibrium, because in that case the equilibrium you can introduce a fugacity, and so somehow it's actually not possible to really separate the system very far from equilibrium in that case. On the other hand, there are phenomena in jets which are also analogous to this actually. So they are, Edmund will talk about this, right? There are turbulent-like phenomena going on in jets which are very similar to this in principle. In principle, there are two sort of, this all goes back to the theory of wave turbulence to a certain extent. And there's sort of two limits of having either, there's different cases you have to distinguish. You have to distinguish. Why are you shaking your head?
An E minus.
Yeah.
And I have 2-to-2 scattering for electrons and positrons. I have an electron and it can emit a photon. It must be a similar analysis. There must be similar conclusions.
Yeah, I mean, well, I mean, I'm not excluding it. I'm just saying I don't know.
No, you just said you talked to Paolo and you concluded you didn't. You couldn't
No,
reach strongly non-equilibrium.
okay.
I don't understand that.
No, okay, so I mean, okay. So here I talked about what's happening in this high occupancy regime, right? And so you can try to do this in the low occupancy regime as well and ask yourself if this is something that happens, right? And my answer is in the low occupancy regime, it actually doesn't happen for that case. Yes. Yeah, and I said this I didn't know, but I said I know that it doesn't happen in the low occupancy regime. Okay, but anyway, I mean, it's interesting to look at, right? Could be looked at. Yeah. I'd like to check first before I say yes, of course, right? But I think we basically all agree.
Any more questions? If not, let's thank Soeren again.